Well, we'll still stay with the engine, and you all must have heard about the knocking and anti-knocking in the engine and things like that. And we also know that just from our general knowledge that there was earlier we used to get the leaded gasoline, and now you get the unleaded gasoline or the green gasoline, and if you go to the petrol pump you see a little unleaded gasoline and things like that. We were using the leaded gasoline for several years. And why was it we used the leaded gasoline, and what we are doing now, we need to understand, because it was largely not the combustion people, not the mechanical engineers or automobile engineer who were in favor of making it unleaded. It was a great revolution by the environmental people, environmental science, environmental toxicology, and they kind of fought this one, and then that's how the technology got changed. And almost like the issue of the lead was so severe that as we see today, all the countries, it costs a lot of money. When you're changing your refining process, you're moving from leaded gasoline to unleaded gasoline. Okay, it costs a lot of money. So you'll be surprised, all the countries, which may be very poor country, now have gone for unleaded gasoline, because lead was a serious problem. Maybe when we talk about health effects and air pollution, then I'll talk to you that why lead was such a serious thing. But anyway, let's first of all understand that what is this knocking thing. Okay, let's see what the next slide really is. Okay, let's start with this one. Okay, and we go by the definition and explain you the figure that as to what is happening. So if you look at the knocking, okay, I'm trying to understand what this knocking business is. In the internal combustion engine, knocking occurs when fuel air mixture in the cylinder has been ignited by the spark plug. Fine, so far so good. And this smooth burning is interrupted. You want the burning to proceed. Like suppose this is you can imagine this is my cylinder, and at the top there is a spark ignition engine, and then it is like the flame will propagate. Okay, we're all talking about seconds and milliseconds and things like that. Okay, smoothly it should expand and should keep on burning and push the piston down there. Okay, that is fine. Okay, just think somehow because of some reason, suppose this is interrupted. Okay, we'll see what, and this smooth burning is interrupted by unburned mixture, which is lying on the back, right? Because that's lying on the back. Okay, unburned combustion, this mixture in the combustion chamber only explode before the flame can reach there. You see, I'm trying to reach there with the flame, and that has exploded. Okay, so what that will happen? So I'm trying to compress something from the side. Okay, and that has already started explosion, and that can compress me backwards. Okay, and then what happens? A knock. And so that is what happens in the engine. Okay, this process is called knocking. Okay, and then what is happening is this smooth burning is interrupted by the unburned mixture in the combustion chamber exploding before the flame front can reach there. Okay, the engineered in other words, the engineered combustion process, okay, that we had engineered for model to work, ceases because of the explosion, because we wanted it smoothly to go, but we failed in the sense because of the explosion before the optimum movement for the 4-stroke cycle. The resulting shock wave reverberates back and forth, okay, in the combustion chamber, creating a characteristics of metallic pinging sound, okay, and pressure increases enormously, okay, and then as a result your engine kind of knocked, it doesn't perform, and you can even hear the sound. Okay, that's what happening. So I want to explain as to why this happened and how it happens. See, hypothetically, let's say this is your cylinder, and I can divide this in 3 parts. Okay, there are no barriers as such, but just imagine there are. So here is the spark plug. So the fuel has started, in this one it has started burning, okay, because you put it this thing, okay. Then as a result this is expanding, so this is the, this B is under compression, so is C under compression, okay. As this photo flame or the flame comes this one, the B also gets on burn, okay. This thing is already burnt, okay. This also gets burned, it's burning, and by the time the pressure, okay, in the C become enormous, okay, because first this portion burns, then this, and then by the time the B, the flame reaches C, and because of the high pressure, the temperature that goes, this auto ignites, okay. So then this was in the compression, so this also explode, so it pushes this explosion the backwards, okay, and as a result you have the knocking in the engine and you don't get the proper power, okay, because this thing. So idea is simple, that somehow you should modify your gasoline in such a way that the time for the auto ignition is delayed, okay, so that it does not if the delaying time, the ignition time is delayed, then by the time the flame front will reach here, and then everything will be all right and you will get the smooth burning. So that was the issue, okay. And then so what and how they could do was, the detonation can be prevented, the delayed the detonation, the use of a fuel with higher octane rating, okay. I'll explain you what is octane rating is, but you see when you go the premium fuel or the octane number is this one, and you may have some vehicles, well, that will run only with the gasoline with octane number so and so, okay, because to with higher is the octane number, better will be the performance of the engine, there will be no knocking. In addition, the addition of the octane increasing lead. There are the other things which you can use, well, so it's called MMT in the short form, that also an anti-knocking thing. But lead is one thing which has been found, lead in the form that I'll show you, has been found to make this explosion delayed, okay, and the delay is there, and then the flame is able to reach, and once it reaches, everything is fine. So what does this lead thing? We'll not get into so much of mechanics here, or let's define the octane number first, because we have used this word. Octane number is the ratio of okay, I can complete that, no problem. This is here. This is the ratio of the octane you have in the your gasoline, and the octane plus N-heptane. Okay, that is the ratio. So this, say again. So this is called octane number. This is the ratio. Does it say so? Octane is measured related to a mixture of isooctane, okay, change that to isooctane, and N-heptane, okay. And listen carefully, an 87 octane gasoline, for example, has the same octane rating as a mixture of 87 volume percent isooctane and 13 volume percent N-heptane, okay. See, the interesting thing is that it may not have any octane, it may not have your gasoline, may not even have the heptane. It is the characteristics of your fuel which matches with what kind of behavior that is there. Okay. So if that is your engine in terms of the knocking, anti-knocking thing is behaving something similar to the performance, because it is standard performance to see the knocking and anti-knocking. So if it is comparing with something which is similar to this 87%, okay, then this fuel may have the, or will be called to have an octane number of 87, and yet it may not have any octane or heptane for that matter. Is that clear? Okay, because as it reads, okay, this does not mean, however, that the gasoline actually should contain these chemicals in these proportion. It is the characteristics of the fuel which is equivalent to having a fuel which is octane, percent of octane and percent of heptane in the order of 87 and 13% volume by volume. Okay, so this is the characteristics. Okay, and octane number sometimes can be, sometimes people report it higher than 100 also. It is the behavior of this thing, and you have only octane, okay, which is like you will not find any kind of knocking. That is, you have no an heptane, then octane number is 100, and then everything is all right. So when we are enhancing the octane number of the gasoline, then we are not playing with this. Okay, we are putting something else, and yet we can say, oh, octane number is changed, as if it appears, like that we are changing this, but we are not changing this. A high tendency to auto-ignite or low octane rating is undesirable in the gasoline engine, but desirable in the diesel engine. Why? Because diesel engine we want self-ignition to take place. Okay, and that number, okay, is defined in the diesel engine by is a C10 number. Okay, we will not get into the details because we are talking more of the air pollution. The standard for the combustion quality of diesel fuel is a C10 number, which is close to around 50. Okay, a diesel fuel with a high octane number, high C10 number. Okay, in diesel we have the C10 number, has a high tendency to auto-ignite as it is preferred in the diesel engine. We want it to auto-ignite. Okay, so you see the difference as to octane number and the, so we have given you the meaning, we have given you the definition of the octane number and the real sense of the octane number also. Okay, this is what is the compound of lead that was used as a anti-knocking thing, and it is mostly by the experiments and the science that people developed that it improved the anti-knocking capability of the gasoline. So tetraethyl lead, abbreviated as TEL, is an organometallic compound with the formula CH3CH2CH4 twice. Okay, it looks something like this. So that was a compound that was used, and that all by many experiments people had done. Okay. And then how this is produced? Okay, TEL uses was largely discontinued because of the toxicity of the lead. It is still used as an additive in the aviation fuel known as avgas. I don't know if it's still true. In my opinion, they should even stop this. Okay, but this is all from the literature. And how it is formed? Well, you don't have to know and remember this. But still, to just get an idea as to how this is formed, you are basically using the ethyl chloride, react with the sodium alloy of sodium and lead. Is it the alloy? Chloride with the sodium, lead alloy, yes. So you make it react with the alloy under certain conditions and you will get the lead. Okay, and then of course some lead is, you get it back and things are balanced, I guess. Yes, they are. Okay, so you produce this and then you mix this one. Remember that all that now we have putting the lead, and the lead will not destroy itself, and in the exhaust you will get the TEL tetraethyl lead, and it's all, most of it, 90% of it, in the particulate form. In the exhaust when it comes out. The problem of the lead and the lead toxicity is, for the timing, just remember my words, it is very severe. I mean, it's very horrible compound or the element. We may have a lot of utility, but you see, body for that matter, we all need some kind of metals in the body, including we need mercury. Okay, including we need all things which you can think of. But lead is one metal which body has no use of. Okay, otherwise molybdenum, we also need some nickel in the body, but lead, people have found that lead has no use. Okay, so lead was a serious problem here, and then it will come in the particulate form. The other problem which I think we need to write and specify is we will see a little later, because how, if you recall or if you know, all, at least from the general knowledge, all in the exhaust, okay, you have the CO and hydrocarbon and NOx. One of the ways to control is to catalytically oxidize this one, okay, and then all the automobiles now has a catalytic converter, especially the gasoline one. So the problem with the catalyst that we used, that I'll show you a picture in a moment, the lead was a poisoning thing for the catalytic converter. Okay, so that the life of the catalytic converter will reduce if you are using the lead in the gasoline, because this will interfere with the catalytic property of this one, and so as a result lead was problem from the health point of view, as well as the performance of catalytic converter would go down. So people thought that lead must be removed very quickly from the system. So lead was removed historically, but we should know that as to why and how it happened. And so this lead story, let's go to something else. This, we are not discussing great deal about this, but still you should have some idea about the compression ratio. Okay, the compression ratio is the cylinder bore diameter, the piston stroke length. This is when this is the volume, okay, which is when the piston is at the bottom. The chamber, this is the ratio between the volume of a combustion chamber and the cylinder when the piston is at the bottom of its stroke, and the volume when the piston is at the top of its stroke. Okay, so what you can say, if I can draw a picture, I guess, and you will agree with me. Don't agree, then ask me the question. Top position, okay, this is your VC, okay, all right, and then this volume, okay, that will be the diameter times, so suppose the diameter is being called here B square, so this volume will be pi by 4, diameter is being called as bore diameter B square, S is its length, okay, okay, and then you can see what the ratio is. Okay. Okay. Now we, as I was telling you yesterday, that the other issues with the diesel engine, we are still staying with the diesel engine. The diesel engine problem was the NOx that we have described at great details and things like that, and we will also talk about NOx a little bit in a moment. But this NOx, okay, apart from the NOx in the diesel engine, you have NOx plus, in fact this is called DPM, diesel particulate matter, okay, that is a very serious problem, okay, that is formed in the diesel engine. Largely expected reaction is one of the mechanisms which people have talked about, because at some point even the CO can be formed, okay, CO is formed in the diesel engine, although it's quickly converted to the carbon dioxide and it can form the CO2. I don't know if this will balance this. Does it? Yes. So this becomes see, you are not finding the carbon monoxide at the end because this is burnt out as well. But CO is formed with the initial stage that can lead to the soda. So people try to stop this formation of this CO, but that can sometimes instantly form in this kind of. So this is one of the routes. The other routes people have talked about, but you can see here this is the oxidation of the carbon monoxide which can result in the soot or the elemental carbon. But apart from that, the particles which you see in the diesel, the general composition looks like this. Carbon, 41%. There will be some ash and other things. Okay, the ash, which is still some ash will be there in the diesel that cannot be burnt, very small amount. There will be some metallic components because of the, all the time the hitting to the metal hitting with the metal. So there will be a lot of emissions of the metal. Diesel will have some metals, okay, that will come out. Okay, the lubricating oil will have some metals. The piston and the piston walls has the metals with this one. Okay, so that will come out, and then some amount of the unburnt fuel oil comes out. Unburnt oil, that is the lubricating oil, that can come out. Some of the unburnt fuel can be come out, and then you also see the significant amount of water. More than the water is the sulfate. Okay. In this process, people have found in the diesel the sulfur dioxide, which is sulfur is there in the diesel. That sulfur is somehow forms to not the entire one, okay, but significant amount. Particulate sulfate. Okay, and let me tell you that we all talk about. With my experience, I can tell you the sulfur dioxide hasn't been a main problem in the country, but still the sulfur has been reduced a great extent in the diesel. To start with, we had something like 1%, like in 1999 or 2000, sulfur content was about 1% in the diesel. Okay, what happened after that one? See, and SO2 was not a problem in the ambient air. But then people with all this combustion people, they could show, and then they all knew from before and from the literature that lots of sulfur goes into formation of the sulfate. So in order to control the particulate emissions from the diesel, the sulfur was reduced, not because this SO2 was a problem in the atmosphere. Okay, and then people talk about the ultra pure diesel and things like that. Right now, in the country, we have something like 0.25% sulfur in the diesel. I think in Delhi, they have even gone below this thing. And finally, they are talking about the sulfur content in the diesel of the order of about 500 ppm. 500 ppm will be how much percentage? 0.05. 0.5. Is that right? The 0.05%, yes, that is correct. So you see, we are talking about 1% to so much reduction, huge reduction, largely because that we want to reduce the formation of the sulfate particulates, not because SO2 is a problem, or SO2 we are finding as of now there is a problem. Okay, this little bit this we had seen yesterday, but let's have a quick look onto this one. That in the exhaust you get the nitrogen, water, carbon dioxide, pollutants. Okay, this what is there, but actually you get the pollutants, unburnt hydrocarbons, carbon monoxide, oxide and nitrogen, and other elements or compounds. That's actually happens. And then of course you are mixing the things here. Okay, and then looks at the losses that we talked about yesterday, that evaporative losses are there from the engine. Okay, the blow-by emissions. Okay, that's what we had discussed last time. And due to the other evaporation, and you see that now people are just, when it comes to the research, people are talking about the emissions from the, or did we change anything here? Wear of the brake. Okay, the problem is that the brake lining, I don't know, somehow many times you can see the brake lining also. You know, they don't have the cover and things like that, you can see the brake lining, and then how the when the brakes are applied, this lining gets wear in, you know, it will be worn out. And there are a lot of metals that comes out, and apart from that, the brake lining is always largely made of asbestos. Okay, so that asbestos particles also come out, so that emission will take place from the brake lining. The other thing which is non-combustion related but related to automobiles is the tire wear. Okay, we will not go so much into the details of this one. You have the tire, okay, and the road surface. Okay, the temperature here, okay, one thing is the emission of hydrocarbons, which because of the temperature vaporize, and the other thing is just because of the friction abrasion there will be particle wear out. Particle wear out is also a very common thing, which you can see the particles, especially when they are braking, this emission becomes very large. We are really talking about significant emissions here. And in addition, okay, all tires, okay, made or has aromatic oil, all will have. Okay, these aromatic oils, just because of the friction, they will give rise to the emissions of what we call as this aromatic oil. Aromatic hydrocarbons. So this becomes another serious problem, which are all cancer causing compounds and things like that. In fact, whereas our technology for the engine has gone so much that we are reducing huge amount of pHs. So once we have reduced pHs and still people didn't find the reductions in the pHs, around the roadside and things like that, they found out that this was largely the wear and tear of the tire that was giving rise to the pHs. One of the students, she is working on to this one as to how to estimate the pHs emissions that can come out from this one. And don't forget, pHs emissions and hydrocarbon emissions can also occur not only because what's in the tire, but from the bitumen itself. Okay, bitumen again organic stuff. Okay, and then that bitumen, the worn out of the wearing out of the bitumen can also give rise to the emissions which people were not considering earlier, but now people are becoming serious, and then there could be emissions from the bitumen also. And then apart from that, we should not forget the metals, which may be part of the tire, because some metals are always there, or on the bitumen, or if it's not a bitumen, it's a cement road. The cement maybe has some this thing, and people are not using the fly ash for that matter. So it's a matter of investigation. I'm not saying that from the fly ash the metals will come out so easily, but then this way. So one of the students here who is doing masters is looking at the metal emissions from the non-exhaust emissions, but related to vehicles and the roads. Okay, so these are little thing which we thought I might just mention it because of the tire. Blow-by emissions we talked about. Okay, this is the burning and the losses, the crankcase losses, the exhaust emissions, and evaporative emissions, refueling losses. Okay, I want to talk about these evaporative losses. That's what we were trying to discuss last time. So about the hydrocarbon emissions of from the fuel tank. As you are filling this thing, there will always be a vapor pressure that will be there. Okay, it has to be there. Okay, so this fuel tank vent line, this is not the fuel supply. Okay, don't misunderstand that it is taken, like depending on the pressure is there. So there's the little pump, okay, that will suck this fumes, and there's a charcoal adsorbent which will absorb the fuel in here. Okay. Alright, but then you can also have the vaporization in the carburetor reservoir. Okay, there also is the emission that can also be sent to this absorbing this one. And as the vehicle is moving, okay, what you do is that you reverse the direction of the flow, okay, and then you're trying to regenerate, okay, from the air. You can drive out these emissions, okay, and then put it back in the engine. Air with dissolved hydrocarbon enters the carburetor below throttle plate when the engine is running, so that this can be utilized. So you see here, otherwise these are the emissions which could be out of 15% or something. So all cars, okay, on all the engines, they will have this facility where you can, and then I also write down from the book what is written here. Control of evaporative emission: the hydrocarbon containing vapors from the carburetor and the fuel tank passes through the charcoal canister. Okay, your car has a canister now, and removes the hydrocarbon before those vapors are vented to the air. So when the engine is running at other than the idle or very low speeds, air is sucked through the canister in the reverse direction, removing the hydrocarbon from the charcoal, preparing it for its next service. Okay, the regeneration of air is returned to the air entry in the engine where the hydrocarbon it contains is burned. Suitable valves maintain the flow in the proper direction. The canister has low enough flow resistance that the pressure in the carburetor float chamber is close enough to atmosphere for the proper operation of the carburetor. Okay. Fuel injection autos have no carburetor. They use the system to control vapor from the fuel tank. The fuel injection automobiles have no carburetor. They use the system to control the vapor from the fuel. I mean, that same thing can also be used for the if you have the fuel injection system where you have no carburetor. Okay, now we're talking about the NOx. We talked a great deal about the NOx emission, but one of few ways in which you control the NOx, and one of the methods which has been talked about and to some extent used also is exhaust gas recirculation. Okay, then I'll try to show you in this picture. Is see here the dark arrows. Okay, this is exhaust. Okay, and then you have something to measure here. The part of exhaust, okay, is taken back, and rest is you can check its smoke. You can pass it to the smoke meter to see what is the smoke density and things like that. That is to see the particulate emission, and rest of it goes through the exhaust muffler and things like that. Okay, and this part of it, okay, and there is a diaphragm here, and there is an orifice plate. You can manipulate as to how much EGR or how much of the exhaust gas you want to recirculate. So part of this is recirculated, okay, and then it comes here, okay, and this is your regular supply of the fuel. Laminar flow equipment, you have the regular supply here, and this is mixed here, and then now a part of EGR, a part of exhaust gas which is recirculated is put into this one, and then people have found the NOx reduction is there because one thing is the oxygen content is reduced, right, and the second thing is that now this gas can absorb some of the temperatures, okay, and then because this is not going to burn, so this is more there to absorb the heat, and once heat is absorbed, so you still get the power, okay, some reduction in the power, yes, but the NOx control takes place because of both drop in the temperature, okay, and you are reducing the availability of the oxygen in the process, and this works. But then what you see, the problem here is, suppose if you don't remove the particles here, because there is a DPM, as I am calling them, diesel particulate matter, they can also be recirculated here, and then these particles cause a lot of problem and wear and tear of the engine, because these particles will be between the two metallic surfaces, they all will be surrounding this one, and as a result the wear and tear of the engine is little bit more. But then people also found because of this the emission of the particulates increases, and then as a result, like the people have to always make a trade-off that you want to control NOx or the particulate pollution goes up. So see here, this is what the people found, This is a temperature and load, and this is a what you see, the reduction in the temperature. Okay, without EGR, temperature was high. Okay, or this is that of the exhaust, and this temperature is, with EGR the temperature is lower even at different loads, okay, of the engine. And then this shows that, well, of course the NOx emission will reduce. The NOx emission indeed reduce. But what the people have found is that with this technique, okay, soot density increases. Okay, obviously because you are recycling the soot also in the process. So soot density increases, and that causes some problem in the wear and tear of the engine. And people have also found that, you see here, the depositions, see, carbon deposits on the cylinder head of the engine using EGR. Okay, and this is without, same kind of engine without using EGR, and you see the depositions, at least you can see here, are much more as compared to what depositions are here. So that is again a trade-off between this. But whatever ways you can find out to reduce the temperature, that will reduce your NOx emission. One of the ways, I think maybe I should explain that. The air, you have the fuel, and then this is going in the combustion chamber, and then there will be a flame. Okay, don't supply, okay, the enough air here. Okay, don't supply the enough air, but supply the deficit air so that you don't have the oxygen to react with nitrogen, and have this kind of baffle, and then supply the secondary air from here. Which can heat this flame here, and then this is a kind of second combustion, if you can say, because the whole thing will not burn here. And temperature won't be very high. Okay, and then as a result, okay, what you get here is a low NOx. But in the process, your size of engine, size of your, I won't call it engine, but this you can do in the boiler also. The size of the boiler increases. Okay, in the boiler you can certainly do this one. Boiler will be slightly bigger. Okay, but in engines it becomes difficult that you can supply the. But there are other ways to how to handle it. But this thing, sometimes people can also air or you will also supply the steam. Steam or water. Water jets are put. What water will do? It sounds funny, you know, like you have the combustion and you're also supplying the steam. What will the steam do, or what water will do, is that specific heat of the water is it can absorb a lot of heat, and yet the rise in the temperature is not so much. That's a specialty of the water. Okay, so it can absorb the heat, and as a result the temperature rise will not be so much. So we have some water anyway in the exhaust, some more water goes in there, what is the problem? So people do use this thing, you know, like, so that in that case we can reduce the NOx formation. Okay, and then we have some special kind of burners, we'll call the low NOx burner. So in this burner, this is like something this you can do in the boiler or something. You also have the low NOx burners. In that case, you have the air and fuel, and then again there is another thing which provides a little bit of more air from the other sides, and then here is again the temperature is dropped. Okay, you burn it. Okay, see, you should remember the heat will be more heat. The amount of the heat is the same. Heat is not changed. It is only the temperature that we are playing with. Okay, the heat is always the same. So you can still make the things you can almost do everything what you want to do, but then you are reducing simply the temperature, because the flame, the high temperature we have seen will favor the formation of NO, or we can say it NOx. Combustion to air to tailpipe. Now we are talking about the catalyst, okay, very briefly. Okay, two-way catalyst, okay, for CO and volatile organic compound or the hydrocarbon vapors. That's called the two-way catalytic converter. Okay, catalyst design and active metal contents are there, and metals, many of the metals are used for as a catalyst in this one. Three-way catalyst is the one which can not only handle CO and VOC and NOx. Okay, so in this one what we want to do is this will require oxidation to carbon dioxide and water, and this will require reduction of NOx back to N2 and O2. Okay, we'll see if the details are there. Catalyst design and active metal content. Location of the catalyst near the engine, that will show you in the picture. Heats catalyst faster to provide emission control sooner, okay, because all the reactions will happen quickly if the high temperature is there. Pre-capture pollutants during the first few minutes of the vehicle operation. Captures pollutant until catalyst is hot. And then we can show you here, okay, how it works. Basically you are supplying oxygen is there, excess oxygen you are working on, or oxygen can be supplied especially for the catalyst, like you don't need an engine, but you can supply this one, CO2 and water, and CO and oxygen, again oxidation, and this NO, okay, is reduced to N2O2, or if there is NO2, that can also reduce in this one. And when we are talking about control equipment in the course, which comes in the later part of the course, that you can see that how the NO is reduced to N2 and O2. This is how it looks like. Okay, your inlet from here, and this is what the structure which is there you see, and catalytic active metals, which are the aluminum oxide, ceramics are there. We also use platinum for that matter. Platinum metal is very useful in here, and but you should and then of course there are some patent on these, but this is how is the catalytic converter. You can put it here, or this is the exhaust system. So this is what at some point, but it depends on different engines where they like to put in the car. Okay, that more or less gives a description of the engine, and I want to do something which maybe we should have done in the atmospheric chemistry part, but this is something not so much in the books. Okay, but let's have a little look onto this one. Okay, what we are looking at, not only simply the organics and ozone, but we also look at the secondary formation of particles, not controlled at source. Formation not fully understood, although now the gases play a role, okay, to produce the particulates of sulfate and nitrates. Function of it depends on the physics and chemistry of the atmosphere. I'll give you some reactions. Okay, as one time I write on the board, ammonia, reversible reaction, you can form the ammonium nitrate, and then you can also find the ammonium sulfate, because you have the SO2 which gets into H2SO4, and then ammonia, and then ammonium sulfate. Okay, so here you can go to HNO3, and either you can react this one with NH3 this way, okay, with the HNO3, okay, and can form the fine mode of the ammonium nitrate. This will be very much in the fine mode. The formation of secondary particles is all given in this one, but you can also form in the coarse mode. Okay, if you have the soil, okay, with the soil it can react, and the soil particles are always much larger. Okay, because these are formed because of the chemistry, but the soil particles are larger, so that also can neutralize HNO3. Suppose you have the calcium in the soil, so you can also form probably the calcium nitrate, but that will be in the coarse mode, the larger particles. But otherwise, if you are reacting with ammonia, it will be in the shorter this thing. Similarly for a secondary particle, so the coarse mode, how it happens is then you have the HNO3, and then you have the soil particles. Okay, it can react with this one and can find the coarse mode of the nitrate formation, because it can also react with the soil, and the reaction, tentative reaction, is here. Okay, when you have the little bit of moisture in the atmosphere, you have the calcium which is from the soil origin that comes, and you just see that can react with HNO3 and can produce calcium nitrate. Okay, and then similarly H2O4 can produce calcium sulfate, and then since these particles are large, okay, because of the soil, okay, they will be, or similarly even NaCl, so this is what you will get the things in the coarse mode. So you have to, you should be able to determine with the chemistry whether this is going to be in the coarse mode or in the fine mode, depending on what atmospheric conditions you are dealing with. Also, if you really want to model the way we model our ozone and things like that, suppose we are trying to model the fine mode, and you see here all this will be in the solid form, or it could be in the liquid form also. So ammonia H2O4 can make the ammonium bisulfate. You can make the ammonium bisulfate, can again impute ammonium sulfate, and it can form the ammonium nitrate. And what we really need to see is these constants. So that we have to very carefully write the equations for this, and then we can solve the equations for what will be, you have the source of ammonia, you have the sulfur dioxide, you have the power plant, and you will be able to say, provided we are able to model it, that well, although there was no emission from the power plant in terms of the particles, because you are cleaning everything, stacks look clean, but still in the downstream you can find a lot of particles, and somehow we strongly believe here that well, it is a major source of the particulate contribution. Still investigations are going on, and then we will, once we study these Ks, Ks1 and Kn and ammonium nitrate, ammonium sulfate, and then how they are formed and what is their concentration and the quantity that we have, then we will be able to see this thing. Like I can also tell you one thing very quickly is this is very volatile. Okay, so if you don't measure it, capture it properly, this will not be even be able to capture on the filter paper if your temperature is high. Okay, so these are the rate constants, okay, that we have seen. I'll pass on these slides to you, and then concentration of the precursors gases. So it depends on ammonia, okay, SO2, NOx. So you should model the formation of HNO3, and then formation of sulfates and nitrates with this thing. And let me show. Try these out, okay. Otherwise, I'll try to send you this reference as well. If I don't, then you just let me know that I have not sent this one. The very same concept that we learned about the pseudo steady state and things like that. You can write the equations of the both ammonia, HNO3, and under different conditions. Okay, whether this is the root or that is the root, and then you can estimate the rate constants. And it has been found that this K depends not only on to the temperature, but also the humidity, because humidity plays a significant role. It also depends on the amount of energy in terms of the watts per meter square that we are getting. It also depends on the temperature. Okay, so once we understand these things, we can model the plume at its travels. Okay, at what distance you will form the ammonium sulfate and ammonium nitrate, and you will find the impact. So this one I'll send you this. If I don't, please remind me that you try to understand everything, because we have covered the theory as to how we write these equations, because eventually we want to predict the concentration of ammonia and ammonium sulfate and ammonium nitrate. Should be the last slide, I guess. So we'll discuss that, or maybe if the time permits, maybe in the next class I'll show you some of the calculations that have been done to show that yes, ammonium sulfate will be formed, ammonium nitrates will be formed. So we'll stop there, but don't forget that from the atmospheric route we can get significant amount of the particulate matter because of the precursor gases, okay, that emitted at the source. Although, so what we need to do is particulates, while we are controlling the particulate matter at the source, fine, but we also need to control the gases if we really want to improve our air quality in terms of the dust, because our conditions are very dusty, and this particular contribution can be very significant. We'll stop there.